Hi everyone, my name is Gianmarco and this is a presentation about avrman, a library written in NIM for bare metal embedded development. Quickly about me, my name is Gianmarco. As I was saying, I'm from Italy, from the southern part of Italy, and I'm an embedded software engineer by trade. I like to hack around on microcontrollers in my spare time, but actually this is also what I do professionally. I work in the embedded area. I'm not only working on microcontrollers though. I also like to write programming articles on Antima.it, which is my website that I maintain together with a friend of mine. I generally tend to write in Italian, but I also translate my articles in English, so most of them are both in Italian and in English, if you wish to read some of those. And my email is this one, if you want to keep in touch, and if you want to find the slides for this presentation, you can find them at my GitHub here. So what I'm going to talk about is that I'm going to talk a bit about writing code for AVR chips and the state of tooling. I'm going to talk and touch briefly on NIM as an embedded software development language and why it's so great, in my opinion, for this particular use case. Going to present my library, avrman, alongside with a couple of examples, and we'll try to cut them up too. And then I'm going to talk about what's next for this project. So let's talk a little bit about the AVR embedded landscape and about platforms. So this is a 32-bit microcontroller era that we're living currently in, but 8-bit microcontrollers still used, still ubiquitous, because they're good enough for a lot of stuff actually, so they're used all around. But they're also a really popular platform for hobbyists, mainly due to the legacy of Arduino Uno, which is probably the most famous board with a microcontroller on it, and it mounts an ATmega 3208P, at least up until revision 4, I think. Also, the other thing about these VR chips is that they're quite easy to use on their own with a breadboard, for example, because they're a lot of time come in through-hole PDIP packages, which are really easy to use. So this is the Arduino Uno. You can see here, probably all of you recognize this. You can see here that it mounts the ATmega 3208P chip. And this is an ATmega 6404 in its through-hole PDIP package. And it's really easy to use in this way here on top on a breadboard. You just put it in. And in this case, I connected an LCD screen here together with a power circuit and a clock circuit. So really easy to use. Quickly touching on some pros and cons about the way AVR is today from a software perspective. It has very nice tooling. I'm talking about its GCC frontend, AVR GCC, which lets us access to all of the goodies in GCC. It has a really nice standard library, C standard library implementation, which also has some AVR stuff in it, like program support, ISRs, IO bindings. AVR which is an incredible tool to program microcontrollers to download data from them. Really, really incredible. Probably the best tool in this tool set. And then, personally, I have a nice debugging story with Bloom. I think there is a nice debugging story, at least with Bloom, which is a really nice debugging interface, which is Linux only. And it's really well integrated with VS Code, VS Codium, and CLion from IntelliJ. Now, some cons. These are quite subjective in part, but in my opinion, C is not very ergonomic. This shows, let's say that it shows its age alongside other, when put side to side with other modern languages. C++ is even less ergonomic in my opinion. I don't like to program in C++ quite a lot. And both of them are hard to get it right, in my opinion. There's a lot of gotchas and a lot of, let's say, pitfalls there. And when talking about C specifically, it has quite a weak feature set, which is by design. But especially when you think about something like metaprogramming, compile time action, it's really weak. So let's quickly talk about NIM to program microcontrollers. I think first of all, at the language level, almost all of the weaknesses in C are fixed by Nim. So what I'm talking about is, for example, rate pointer decay, the fact that it has a stricter type system, which is also more ergonomic. The fact that it has array access checks, which are tunable, by the way, and the fact that it has hygienic macros and bit fields. I'm going to show you a couple of usages for those in some slide later. So another couple of nice Nim features. First of all, is that Nim allows you to use low-level primitives. This is important, fundamental for programming this kind of stuff, because you need things like casts, you need stuff like pointers, and also inline assembly is another thing that Nim provides. It's really easy to check generated C code. So Nim compiles to C, and you can just check the C code. It's not, one you would write, but it's quite easy to check. And also it has tunable memory management strategies. I tend to use either just no memory management strategy, so I just turn it off, or I use arc, which is really nice for embedded because it's deterministic, so nice for real-time stuff. And then, in my opinion, the killer feature for Nim is compile time and metaprogramming, which is out of this world, in my opinion. Really nice, really nice. I talk at length about all of these topics in this article here that I'm linking in the slide. If you wish to know more about these features, please encourage you to read it. But I'm not going to focus on this. I just wanted to talk briefly about this because I think it's important. So AVR-IO. AVR-IO is a library that I wrote in Nim, which brings binding and utilities for AVR microcontrollers in the language. It requires Nim 206 at least. It needs AVR GCC installed in your machine, as it's C backend compiler, so you have to install this if you want to use the library. But there's no really other dependency from a code standpoint, because it's quite self-contained as a library. And you can find it here on my GitHub. In my GitHub, you can also find a lot of other complete and functional examples, some of which I will show you in the slides, but there's a lot more. So you will find a lot of examples that are functional and are working. And let's go into it. So the first thing, the most important thing, which is what I started with when writing this library, was that I wanted to offer memory mapped register definition for your microcontrollers. In this case here, you can see that this is how I would define this at the library level. And whenever you import, whenever you set up your project with a specific microcontroller, you have access of all the registers defined for the specific microcontroller to use in your code. And how would you use it is something like that. So you import AVR-IO in your code, first of all, and then you can see you can write into a register by dereferencing and assigning. So in this case, we are doing this on the direction register for port B, DDR-B. And then you can also read by just dereferencing it, the register, and you can see here that I'm both reading and writing to port B. So another thing that lies at the foundation of the library is interrupt vector definitions. You can see here that I'm defining some interrupt vectors here. And the way that you would use it is that you just use it to tag a procedure which has to have no parameters and no return type. And you tag it with macropragma, the ISR macropragma. And then you specify whichever interrupt vector you want this procedure to be called when that interrupt is fired. In this case, you can see here that whenever this is fired, we're going to toggle pin 5 of port B. And you can see here we're using this toggle pin utility. AVR-IO supports gives you a lot of APIs like that, which are really templates. So you're not wasting any CPU, let's say, spins when using those. These are just templates. And here we have the set enable macro, SEI. You also have CLI, which is the clear one. And the first one, this one here, you use to enable globally interrupts, and the other one disables interrupts globally. So the library also supports program memory. you just tag let statements with the program macro pragma, and the library will put this stuff, the compiler actually will put this stuff into program memory instead of allocating normally. And you can see that this works for floats, for numbers, 8-bit, 16-bit, 30-bit, 32 bits, strings, arrays. But it also works for objects, both normal, plain ones, and nested ones. And it works just the same way as earlier. You just tag them with program. The library also offers a system module. This is mainly containing various stuff that can be used for implementing bootloaders and for specifying where to put data into the binary that you're generating. Like, for example, here I'm showing how to put some data into the metadata section in the URL binary. And you can see I define a compile time function that will fill an array with some value, compile time. And then I just put it into this header here. And I'll tell nim to put this particular variable inside the metadata section. And you can see here that this actually works. This is a VR object dump on this specific section. You can see that the data is different because there is a script that modified this data in a pipeline, in a build pipeline. But that's how it would look. So now coming to peripheral support, this is partial right now, an experimental thing that I brought into language starting from the last release. This is not something that was thought from the beginning, but I really like that I'm adding it now, and mainly focusing on UART, USART, and timers right now. So for example, I'll show you the first one, and I'll show you how it works quickly. Essentially, you can see here that we can define with this template a baud rate here, specifying the baud rate here. And you then initialize the USART peripheral. Now, first of all, you can see the USART 0 is already in scope here. And this is something that essentially it works like for the register definitions. If you're using a specific microcontroller, then you will have all of the peripheral already in scope to use. And then you use init UART here, this function, you specify a baud rate, but you can also specify the flags for the specific control register of the peripheral. So in this case, you use bit fields for this. So these are all defined as enums, and then you can use them as bit fields when initializing. This is one of the greatest things about NIM. It's really ergonomic, it's really nice to use, and type safe too. So I generally always do it like this. Then here you can see that I have a buffer, and I use this buffer to read some data from a serial port, and then to send it back. So this is a simple echo server with this library. Then timers. Here I'm showing you a little bit about how to use them, and you can see here that as for the other peripheral, we have the timer 0 which is already on scope, and same thing about the bit fields, right? I'm using those to initialize the control register for the timer, and also you can see the OCRA register is the reference and assigned. So this is just like any other register that you would use directly in the previous examples. So that's it for the core features. I'm going to talk a little bit about the limitations of the library, the current limitations. So first of all, this supports only a subset of AVR chips for now, which are mainly 80 mega chips that I have on hand and I can test myself. But the process to add one MCU to the list of the supported ones is semi-automated, so I anticipate that in the future I will just support all of them. It works right now only with AVR GCC, so I have a plan in the future to actually support any other compiler, but for now I'm focusing on this one. And it requires, using this library requires a bit of project configuration, which I'm going to get into right now. So first of all, you have to provide a panic override.nim file, because we are really not using an OS. Generally, we use OS standalone or any. And when defining a panic override, you have to provide the exit function, the row output function, and panic. And this example that you see here is based on the nim test suite, the AVR subdirectory, so you can find it there. And this is a little bit modified. Also, you have to specify a couple of flags in your configs. So this is my config.nims, a template that I generally use. You can see that you have to specify this define using ATmega32.8p. This is the one that is used by the library to understand which chip you're using. And also you have to pass some flags to the compiler linker for C and specify which compiler linker you're using. Then you actually have to specify the CPU line 2 as an AVR. And first and third row actually are debatable, meaning that you could use OS any. I think it's the most modern alternative in the compiler. You should use that probably. And right now I'm not using the GC, so I just disable it. So since this is a little bit boring to do manually, I created a tool which is avrman, or the AVR manager. So it's not an AVR dude, it's an AVR man. And it's a tool to manage AVR projects. It can initialize both name and C projects actually. And AVR IO is used as the base dependency for NIM ones. It supports make and CMake for C projects, so it will initialize with some templates a make file and a CMake list.txt file for your projects. And you can find it here on my GitHub. So how do we use this? For example, I'm going to initialize an Arduino Uno based project here. And you do it by saying avrman init. You specify the chip here, the part number, and there is a list on GitHub of this part number supported by the tool. Then you can specify a frequency, which is non-mandatory, and also prog string, which is also non-mandatory, and then the name of the project. And if you want to use it for generating a C project, you can do this by using --C project. And if you also add --CMake, you will initialize a C project using CMake instead of make files. If you take a look at the Nimble file that is generated for you by the tool, you will see that you have a couple of tasks, additional tasks. One is this after build here that will generate the hex, elf, and binary and .bin files from the compiled binary. And the other one is just a clear task. Then there's another thing that you can do. If you specify here a prog string, actually avrman will actually generate also flash targets to upload stuff using the prog string you provided there. Okay, so with that in mind, let's try to implement a simple blink application on an Arduino Uno, and we will blink the inbuilt LED at a frequency of roughly 1 Hz. So I have the full working code here on my GitHub. If you want to look at it, it's fully working. You can just plug in your Arduino and this will work. Probably you will just have to change the prog string if you're on Windows or other systems. So let's initialize the library. Like I told you earlier, this is actually the same command as earlier. And this uses Nimble behind the scenes, so you will need a Nimble installation if you want to do this, if you want to use avrman. And now a little bit of math, not too much. The Arduino Uno has a clock frequency of 16 MHz. So in order to make this work, I'm going to prescale it by a factor of 1024, which will yield this frequency here. And if we just compute the period that this yields, we get a period of 64 microseconds. So if we want to have an interrupt every roughly, at more or less 1 Hz, we don't care about being too precise, you can just plug in 10,000 as a value for OCRA, and this will yield us an interrupt which will fire every 0.64 seconds. So let's just code this, and you can see here that I defined the built-in LED as the 5th pin in port B, and here you can see that I have I'm using the OCR A high and low register and put there our 10,000 value. And then I'm going to initialize the flags here. So the first one is the B flag, the first one, which will be initialized in order to have the prescaler of 1024 and the specific timer mode we're interested in. And then we will also use the OCIEA flag to say that we're interested in the compare A vector timer interrupt. So then we can tie those two together actually by using the ISR macro pragma with the timer 1 comp A vector here. And you can see that just a simple procedure, this will toggle the pin, nothing special. Then we write a simple main function where we initialize the LED pin and the timer. We enable interrupts and then we do nothing because everything will happen in the interrupts. You can see here that I have actually a demo, and you can see that I program the chip here, and then you will have this blinking at more or less 1 Hertz. Okay. So this was a simple example. Let's try something a little bit more complex. And I like, you know, all the video games, retro video games, and I also like playing music a lot. So one of my you know, passions is to blend these two, and one way that I do it is I find these old, you know, 8-bit chips for audio generation, and I try to use them for you know, small projects. So in this particular example, I'm going to use an AY38910A, which is a programmable sound generator from the 80s. And you can see the full working code for this on GitHub too. Okay, so this works already like this, and it's functional if you have the chip. So this is the PSG that I'm talking about. It's a 40-pin through-hole PDIP package, and I'm going to show you how this works. Essentially, you have a bus, a data and address bus here. And you have a couple of control signals that will switch the mode of operation of the PSG. And then you can pass the data through this bus here. Then you have 3 output channels where the waveform will be generated and outputted. And then you have a clock signal that you feed into the chip. That in this case I'm feeding as a 2 MHz square wave. The clock signal is important because it gets used as the source to generate the final waveform. And the way this works is that this signal of the clock signal gets scaled by a factor of 16. And then it gets scaled by an additional factor depending on the value of a 12-bit integer that you pass through the data bus. This means, with a little bit of math, that if you have this 2 MHz frequency, you have a range of frequencies from 30.5 Hertz to 125 kilohertz, which is roughly from a B0 to a B8. For our Italian listeners, this is a C as a note. And in general, to play a specific frequency with this chip, you can, and I'm actually using the equal temperament system here. I want to play with the equal temperament system, so each note has the same space between one another. This is the formula that regulates this. So in the end, at the last row, you get a formula for the coefficient, or the 12-bit coefficient that you have to compute to get the specific note that you want. The note here, this coefficient is a function of how many half steps you're away from a central tone, which in this case is 440 Hertz, A in the 4th octave. So I want to have a table of coefficients to play each note in the supported range, and this is where Nim shines, one of the things Nim shines. So I can write a compile time function that will generate an array with all of these values. So I implement the mathematical formulas that I introduced earlier with a couple of templates. And then I write this procedure, the generate magic notes procedure. It will just use those templates and iterate over the half steps between all these nodes and create this table. And that's it. That's one of the best things about Nim. You don't have to use a separate tool chain. I would have to use Python in the past to do this in C, generate this with Python and have it separately. And then if I had to change anything, I would have to repeat all of the process. Here is inbuilt into the project. And then you can just write const magic nodes equal generate magic nodes. And this will be executed at compile time. And it's just done. It's as easy as this. Now let's try to make use of those nodes that we generated. Let's write a simple object for the PSG. And you can see a couple of points here, which is, first of all, I'm using a macro here by ref. This is something that you can use to force the object to be passed by reference when passing it to procedures, which is a macro optimization maybe, but I wanted to show this to you. Also, I'm using ports here. This is a type from AVR.io, which describes a whole port in a microcontroller. So avr/io.h in avrlibc offers a couple of delay functions, which we kind of need now. And it's really easy to wrap those in a NIM procedure, thanks to its fantastic, powerful foreign function interface. So you would just do it like this. Okay, you define the procedure, just the signature, and you just do import C with the name of the function in C, and wherever it's found in which header. And it's as easy as this. You can just use this. But another thing that we can do is that we can also implement something ad hoc with inline assembly, because NIM allows us to do that. And as you can see here, I'm writing this in assembly here, directly from NIM. And there are some rows that I'm not showing because it would be too huge, but you can find this on my GitHub completely. Okay, now we can write a couple of mode selecting functions for the PSG because we needed that delay function. And for example, we can write a write mode. So this PSG has 3 modes. It's not important to go into this detail, but we can define them as templates. And templates here are really used as real inlining, okay? So whenever you want real inlining, you can use templates. And differently from C, these are scoped. So, they are not dirty by default. So everything defined inside the template will not clash with the stuff from the outside world. And you can see here that I'm using the clear pin and set pin templates on this port here that was defined in the object we talked about earlier. And these are other templates that I'm exporting that allow an easier use of ports and pins facilities. So these are always templates, so they're not really, they do not have runtime costs. And here we use the delay function that we defined earlier. Finally, we can write some data to the PSG bus, and we do this by using the mode selection, and also using this set port value, which is a template that writes a whole, 8-bit integer to a port you specified. So together with this, we can finally implement the high-level APIs for the chip, and we define a couple of enums to do this. First of all, you can see here that channel mode in particular has a couple of nice properties. You can see that I'm using a pragma that let us define the exact width of the enum. And also I'm using bit fields. And the way that you use them is at line 14. You use set on the enum that you defined, and this lets you use enums in a type-safe way as flags. Then I start implementing 3 of the 4 APIs I'm interested in. So how to open a channel and to close it, and how to set the amplitude of a channel. And you can see here that I'm using the previous primitives. Alongside with the other operations, so like NIM offers the bitops module that implements some nice bitwise operation for you. And also here I am using this toMask template, which I defined to switch from the bit field to his underlying integer representation. So mainly that's it. And then we implement the play note function, which uses the constant nodes, the constant table, compile time table we generated earlier, at runtime to actually play the note. Finally, we have to generate the signal for the clock, and I generate it through the timer. So I'm going to just use the timer in compare output mode, CTC, and you can see here that I'm still using bit fields to set the control register for the timer. Okay, so let's just program the synth to do a note sweep, which is my kind of hello world for this. And you just have a simple main function here. You can see how you use the channel on, for example, API. You would use this with a bit field with the CH8 tone enum, which we defined here, right? So you can just use this, and this is type safe, okay? And then what else? You can see here another nice thing in Nim. You know, we can use for with ranges, quite nice. And yeah, that's just it. So let's see it in action actually. You see that the program. So this is quite an easy setup using an Arduino Mega here. So the code is actually based on an Arduino Mega, ATmega 2560. And this is the setup for the chip, right? So you need to have this circuit here, which I will include in the GitHub repo. And I'm using a small amplifier with, this setup here to actually hear the notes. So this shows that you can actually use Nim for even a little bit more complex stuff, and it's also easy to separate in the library between where you're actually using the really low level even unsafe stuff, and where you define more high level APIs, and you can actually have a quite fine-grained control about performance, about code generation. So what are the next steps for this library? Okay, first of all, I talked about how I'm supporting only a couple of MCUs right now. My idea is to support all of the AVR Dude supported ones. So also want to add other peripherals for sure. I would like to at least complete the peripheral set for the MCUs that I support right now. And I would like to add far pointer program support. This is to completely freely use program stuff on chips with more than 64K program memory. And also I would like to make the system macro, a couple of system macros for vector relocation and similar stuff. This will go into the system module. So I would like to make this a little bit bigger and more ergonomic to use for our users. Yes, so all of this takes place in GitHub. So issues are open, and if you wish to use this or contribute this, I'm more than happy to talk and discuss anything. And that's all for my presentation. I hope this was helpful and that you will use it in the future. And thanks.